In this video, we present our work, FisherMatch, Semi-Supervised Rotation Regression via Entropy-based filtering. Incorporating neural networks to regress the 3-degree of freedom rotation from a single image is an important yet challenging problem. It becomes one of the key technologies in a multitude of applications, such as object pose estimation, camera localization, and robot grasping. One major obstacle to learning-based 3D rotation regression is that most works rely on a large amount of labeled data, while rotation annotations from single images can be extremely laborious and expensive. To reduce the need for a large number of labels, we consider semi-supervised learning, which has been a powerful approach that leverages unlabeled data to improve model performance. Although semi-supervised learning, especially on classification, has witnessed rapid progress in recent years, there is no existing work on semi-supervised rotation regression, which we believe is a very unique and challenging problem. We all know that it is undesirable to turn the rotation regression into a classification problem due to the unavoidable discretization error. Given semi-supervised regression is very underexplored, rotation regression is even not a standard regression problem with the non-Euclidean SO3 output manifold. To tackle the challenges above, we for the first time propose a general framework, namely FisherMatch, for semi-supervised rotation regression. We leverage a popular teacher-student mutual learning framework proposed by FisherMatch, which we briefly revisit here. This framework contains two models with the same architecture, a trainable student and a non-trainable teacher in charge of generating pseudo labels. One important mechanism in FisherMatch is that the predictions from the teacher are filtered based on their confidence, and only highly confident labels will be used as pseudo labels. Fortunately, a classification output naturally carries the confidence information. When comes to rotation regression, a research question is how to measure the confidence. As pointed out by the literature, probabilistic modeling of rotation is the correct way to naturally model the uncertainty of rotation regression. In this work, we investigate two parametric distributions of rotations, namely Bingham distribution for quaternions and matrix-Fisher distribution for rotation matrices. For now, let's assume matrix-Fisher distribution. Training labeled data is simply done by maximizing the log likelihood of the data. To model uncertainty, we further propose to use the entropy of the predicted probabilistic distribution. Here, after training our matrix-Fisher-based rotation regressor on the small labeled data, we observe this histogram on validation data. The blue columns are below 10-degree error, the oranges are between 10 and 100-degree errors, and the greens are more than 100. The x-axis is the entropy. The lower it is, the more confident this prediction is. We can see that the entropy clearly indicates the prediction errors, which allow us to set a fixed entropy threshold tau, and only reserve the predictions with their entropies lower than the threshold as pseudo labels. For unlabeled data, both our network predictions and pseudo labels are distributions, which renders a new supervision problem for our pipeline. We investigate two types of losses, namely, cross-entropy loss and negative log likelihood loss. Here comes our full pipeline, namely FisherMatch. We leverage a teacher-student mutual learning framework that is based on matrix-Fisher-based rotation regresses. For labeled data, the student network is trained by the ground truth labels with the supervised loss. While for unlabeled data, the predictions of teacher model first go through our proposed entropy-based filtering mechanism, and the confident predictions will serve as pseudo labels. To enforce loss between distributions, we use CE or NLL loss. We evaluate our algorithm on common benchmark datasets. We find matrix-Fisher distribution yields a better regression accuracy than Bingham distribution, since rotation matrix is a continuous rotation representation while quaternion is not. Our experiments show that CE loss performs slightly better with broader compatibility. Notice that NLL loss is a sharpened version of CE loss, and thus may yield overconfidence, especially with a tolerant entropy threshold. We show results on ModelNet 10 SO3 dataset. Our method achieves a significant improvement over supervised learning and other semi-supervised learning baselines. Consistently, our algorithm outperforms all the baselines on Pasco 3D+ dataset. Note that our algorithm works well even with very few labeled data, for example, when only 7 images are labeled. In this work, we propose FisherMatch, the first general framework for semi-supervised rotation regression, which achieves superior performance. Our simple and effective algorithm could be plug and play on any tasks concerning rotation estimation. Our code is released. Thanks for watching.